Welcome to the 28th lecture video for Physics 4C. We start our semi-historical introduction to particle physics with this lecture. While our textbook starts chapter 11 with the current state of the art, the standard model of elementary particles, we will introduce each discovery in a roughly chronological order, in order to build a narrative that will help us remember the salient details. We do need to introduce the Feynman diagrams out of historical order so that we can diagram relevant interactions in a standard way that will be useful later on. With the introduction of the Feynman diagrams and illustration of how this tool helps us ensure that we follow the required conservation laws, we return to a particle interaction we saw earlier, beta decay, to point out a quantitative feature where our earlier calculation disagrees with the actual experiment. This will lead us into the first elementary particle we introduce that you have not seen in your previous science classes, the neutrino. And this also introduces additional quantum numbers that are conserved, as well as how the neutrino in the beta decay of a neutron is actually an anti-neutrino, and what antiparticles are in general. All the particles discussed in this lecture are leptons and baryons, and force mediator bosons. In the next lecture, we will introduce mesons and start to a pattern that culminates in the standard model of particle physics. What I want to actually go over before we start talking about particle physics is one of the tools we use to illustrate interactions. So just so that you have reference to the written material, if you are looking for, well, where is all this written up? In your textbook, it's actually in chapter 11, section 5, where it talks about standard model, because this is how we illustrate things. It's the thing called the Feynman diagram, and this is an example of a Feynman diagram. And I will kind of explain what all those lines are supposed to mean. But let me start from there. This is the free body diagram of particle physics. So when we were doing mechanics, one of the earliest things in physics 4A, one of the earliest things you introduce is the free body diagram so that you have a way of illustrating the system you're dealing with. This Feynman diagram is a way to illustrate the interaction you're analyzing so that you can, you don't have to be as wordy in describing what it is you're analyzing. So let me talk a little bit about Feynman diagram. By the way, this is obviously named after a person. How many here know about Richard Feynman? Have heard of Richard Feynman? He worked on the Manhattan Project. He's dead. He died in the 80s. He worked on the Manhattan Project, the A-bomb, as a graduate student, and he won Nobel Prize on something. I guess his path integral method of something. And he was a professor at Caltech, I guess, until he retired and died. So the reason I bring your attention to this particular name, I don't often do that, is because he's probably one of the best science communicators, even until today. So if you are just so he's known for some of the publications that's meant to be accessible to general public. So I guess probably the best known one is, surely you are joking, Mr. Feynman. So it's meant for people who have no training in physics. So it's certainly accessible to you. And the other writing that he is known for, which is really good reading for physics and engineering students, is physics. I guess we call it Feynman lectures on physics. What it is these Feynman lectures on physics, it covers in 3 volumes. It covers the same physics we cover in physics 4A through 4C, but in a very non-traditional order, because they cover radiation and heat in the first volume. And I would say, if you feel like you understood physics well enough, this will help deepen your understanding, because the way he covers is different from the standard approach. I remember as did I do it as undergrad? Reading through volume one summer, and it helped me understand a lot of things that I didn't quite understand fully. So, yeah, I just wanted to bring your attention to that because he's one of the best science communicators. I think I made it no secret of me being quite dismissive of a lot of popular science writings and stuff out there. Because even people who are actual physicists, like Brian Greene, a lot of his stuff is just garbage. A lot of Nova series is just garbage because they've dumbed down the physics so much that whatever it is they're communicating is no longer physics. But Feynman doesn't do that. So a lot of his stuff, whether it's meant for lay people or people not trained in physics and engineering, or if it's meant for physics students, it's pretty good. So Feynman diagram, what it is, so it's a tool to analyze interactions. And even though it can be used to analyze many different types of interactions, most of the interactions that can be analyzed using Feynman diagrams, they are going to be analyzed as collisions. As in, you imagine two particles coming together, they collide, and then something happens. So this is how you can imagine it. So this diagram is illustrating collision between two electrons. So an electron comes in, so electron 1 comes in, electron 2 comes in. They somehow interact with each other. We would say right now by Coulomb repulsion. And they repel each other, and electron 1 goes different way, electron 2 goes different way. So that's the basic idea. But what I want to highlight is that this is it's a schematic diagram. It's not meant to illustrate the actual paths of particles. For example, if this is electron, and if this is a positively charged particle, like a positron that we'll talk about later, we will still draw it the exact same way. Even though an electron and a positron would attract to each other rather than repel, we would still draw it the exact same way because it's only a schematic diagram. It's not showing you the actual particle paths. So let me just start out you with some examples, I guess. Let me start you with an example that will be more familiar to you because these are examples we have mentioned when we were doing special relativity. So one of the, I think, homework problems or something that you have seen, one of the examples is in relativity. Let's say you have two photons coming together, collide to make a single particle of some mass m. Right? So before Feynman diagram, this is how we drew them. So I guess let me just call it regular diagram. And with a regular diagram, there are no rules. You just draw whatever it is you want to draw. So you draw, well, there's a photon coming in and another photon coming in. They collide and make some particle of mass m. That's how you might draw it, right? Different people will draw it differently, and that's fine. So in a Feynman diagram, this is how I would draw it. So in a Feynman diagram, one of the rules is for known particles, like photon is a known particle. There are very specific ways of drawing their lines so that just by looking at the diagram, you know what kind of particle it is. In fact, the way it's drawn here is meant to represent that. Photon is supposed to be drawn like a sinusoidal wave. You can kind of see why, right? It's like a circuit diagram. In a circuit diagram, the inductors are drawn as coils because that's how most inductors are. It's some kind of coil. So when you are drawing a photon line, you are trying to represent an interaction that involves a photon. You draw it as a squiggly line. That's meant to be like a sinusoidal wave. So this particular interaction as a Feynman diagram will be drawn as a photon coming in. So here's one photon. And here's another photon coming in, second photon. And they interact at a vertex. The vertex is what represents it's what represents interaction. And out of that interaction comes a single particle that is particle of mass m. And if you want to be extra clear, you can label the lines. Photon labels are less necessary, but I can still label them. There's nothing prohibiting me from doing that. And I guess while this is not strictly required, you can, there's a traditional way of organizing it. The traditional way of organizing it is you use one of the two axes, either the vertical or horizontal. I'm just going to use the horizontal one. That's what I think I'm supposed to be used to. So I'm going to use the horizontal axis to illustrate passage of time. But once again, it's in a strictly schematic sense. So by letting the horizontal axis represent passage of time, what I'm really saying is that what's on my left side is the initial state, and what's on the right side is the final state. Because in this regular diagram, it's maybe it's not so unclear. It's not necessarily clear if I started out with this or if I ended up with this. But in this Feynman diagram, just the orientation of diagram alone says, well, I came in with 2 photons, and I have an outgoing single particle of mass m. Good. So this is a kind of basic way Feynman diagram is supposed to be drawn. And let me fess up to one thing. This is actually a wrong Feynman diagram. If you are to look at real Feynman diagrams, you will never find the Feynman, never? Ever? Yeah, you will never ever find a a portion of a Feynman diagram that looks like this. And there's a big reason why. Let me explain why. And this matches with what I said earlier in class at some point, that energy conservation is absolutely held. It's never violated. And it's in this context I was referring to. So all the conservation laws we know, they are enforced at each vertex. Each vertex enforces all required conservation laws. We probably should start keeping a running tally of conservation laws. Your textbook does cover this in some later section, but I think this is a good time to just start listing everything we know are conserved. So if you are looking for it in your textbook, it should be somewhere here, particle conservation laws. So you can look at that there. But let's just start listing all the conservation laws we know, just so that we are sure that we are not violating any of them. So the list of conservation laws. What are some things that you know are conserved? Energy and momentum, those are the two big ones. Those are sometimes known as 2 pillars of physics. So energy and momentum are conserved. Or if you are special relativity minded, then you could actually combine this into one quantity and say that 4 momentum is conserved, because these are the components of the 4 vector, that momentum. What else is conserved? Mass? Now, mass, it turns out we can't say that is conserved, because when you say mass is conserved, we are trying to say rest energy is conserved, and that's not quite right? We know interactions where rest energy goes into kinetic energy. So we won't say mass. So one thing I can say is that mass conservation is not held here, because, well, it's not conserved. Okay, what's conserved? I think there's one more quantity that you are supposed to know is conserved. It's possible that you are not thinking of it as a conserved quantity because you think it sounds like one of the other quantities already there, but it's actually a separate quantity because the fundamental reason it's conserved is distinct from why any of these are conserved. You covered this in physics 4A, actually. Yeah, angular momentum. And I know many of you aren't thinking of it as a separate thing, but momentum and angular momentum, I know they sound similar, but they're different. So we have to list angular momentum as a separate quantity that must be conserved. And this especially makes sense in the context of quantum mechanics, because spin is its own thing. Like spin has no linear momentum it's associated with. It's just an angular momentum that exists independently of momentum. And actually, I guess we are not going to spend much time on this. Each one of these conservation laws, they are associated with a natural symmetry that exists in nature. So this gets too abstract, so I don't want to waste much time on it. But for those of you interested, look up something called Noether's theorem. She was a mathematician. I don't know if she was, I want to say German, but I don't know. Well, okay, I don't know her nationality, but it's a theorem proved by a mathematician who says every one of conserved quantities is a result of a symmetry in the physical system. So I will just list the symmetries that are responsible for each of these being conserved. And I guess let me call it natural symmetry. So the symmetry that's associated with energy conservation is a symmetry with respect to time translation. You can think of it this way. The experiment that you do today, if you did it tomorrow, you should still get the same result. So that's what we mean. We have time translational symmetry. When you translate a system in time, nothing changes. So that's directly related to energy being conserved. Momentum is associated with spatial translation. So in fact, you can kind of see some of the systems you have seen. So if you have a cart that's just rolling on a flat ground, momentum is conserved in this system, right? What kind of change can you make to this system to make it so that momentum of this cart is not conserved? What change can you make? Any change? You could add, you can add friction, but it's hard to address that in a symmetric way. So the easiest way to do it, add an incline. Then once you have an incline, it's no longer symmetric with respect to translation in horizontal direction, because as you go, the height changes. So when you break the symmetry, then the horizontal momentum is no longer conserved. So that's what's associated with momentum. Any guesses what symmetry is associated with angular momentum conservation? What kind of operation, what transformation that a system must be symmetric with respect to that would lead to angular momentum conservation? Something radial, right? Now, would you want it to be synced going like a movement radially outward, or movement kind of in a tangential direction, a kind of rotation? Tangential, yeah. So angular momentum is associated with rotational symmetry. Symmetry with respect to rotation. I guess I could say angular rotation, but I think when you say rotation, angular is implied. So these are very common symmetries in nature. In fact, if you take the universe if you take laws of physics as a whole, these are obeyed every single time. When you take a look at like Newton's law, when you translate the system with respect to time, Newton's law doesn't change. Same thing with the spatial translation, same thing with the rotation. When you look at any kind of expressions for kinetic energy, all these are held. And that's what results in, those symmetries result in these conservation laws. All right, so those are the big three that you already know. There are actually more that I think you can kind of guess at it. There's at least one more that you should be able to guess or remember, maybe. One more quantity that's conserved.
Electric charge?
Yeah, electric charge. So electric charge is the other big quantity that's conserved. And as for the symmetry, which is associated with this, I think it's a gauge transformation symmetry. I won't get to that because we haven't talked about, vector potential in electromagnetism. But there is some symmetry that's associated with charge conservation. So these are the four big conservation laws that you already know. And based on this, I can tell you that this particular Feynman diagram is impossible. Because whatever this is, all those 4 conservation laws have to be obeyed. So energy and momentum conservation, am I going to get in trouble with any of those, or am I fine? Like in this interaction, so energy conservation is probably okay. I can just make sure that this has correct mass. Momentum conservation, am I okay with that?
Is it spatial, so would you have to do it over the horizontal and the vertical axis as well?
Well, we can consider a special reference frame. So one easy reference frame to use is the center of momentum reference frame, where this particle will be at rest. Now, can you imagine an arrangement of photons that will conserve the total momentum? Right? Head-on collision, equal energy, so momentum adds up to 0. So you start out with 0 momentum here, end with 0 momentum here, you will be fine, right? Okay, I can conserve energy and momentum. Angular momentum, let's say, yeah, we can satisfy that. The problem is electric charge conservation. So according to that 4th conservation law, what must be the charge of this particle? 0. All right, so maybe you think, oh, so that's fine. We'll just have this charge be, this particle have 0 charge. Then there's a very subtle problem with this diagram. Anyone guess at the problem that I'm hinting at? It's not that obvious. You kind of need to have it pointed out to you. It comes down to that Feynman diagrams are supposed to represent interactions. Okay, so if your interaction involves a photon, what kind of interaction are we talking about? What kind of forces are involved in this interaction? What is a photon at its very nature? Yeah, electromagnetic wave. So if you have a photon involved, then what this means is this is some kind of electromagnetic interaction. Okay, what physical quantity do you need in order to have electromagnetic interaction? Okay, you can. So what photon actually represents is electric field. So if you have electric field, what else must you have? Okay, you can also represent the magnetic field, all right, but okay, let me change the question. If you have electric field, where did it come from? What produces electric field? Yeah, electric charge. So to produce electric field, you need electric charge. And if you have electric field in empty space, like nothing would ever happen there. For the electric field to interact with something, exert a force, what do you need? Like what kind of objects do electric fields exert a force on? On electric charges. So if it's an electromagnetic interaction, it requires charge. So if this hypothetical particle was a charge neutral particle, as conservation law requires, then this interaction couldn't happen in the first place because the photon wouldn't interact with a chargeless particle. So that's what I mean. This is kind of a fraudulent diagram. It's a diagram that actually doesn't exist. And I guess that's a problem with anything that's hypothetical, because you are drawing diagrams based on things that may not exist. So the diagram you end up drawing might be something that doesn't exist in the first place. Let's be more real and actually talk about a real interaction that takes place. I think we have some list of interactions that we can draw from. I think the easiest one is probably the Compton scattering. Somebody tell me what Compton scattering involves.
When a photon hits an electron and bounces off the
Yeah. A photon scatters from a charged particle. We can call it electron. Let's say it's electron. So in a Compton scattering, this is kind of the reaction diagram you might draw. A photon comes in, collides with an electron, And then, well, actually, I guess nothing changes. You still have a photon that bounces off, and you have electron that also bounces off. So this is the kind of a reaction equation you might draw, which doesn't seem like a lot, but all right. So that's the Compton scattering equation. And we can, to give more physical detail, we can draw a Feynman diagram. So let me just illustrate the process for drawing this Feynman diagram. Well, what you can check that whatever diagram it is you're drawing is correct. You can look at your initial state and your final state. Do I have a photon and an electron coming in? And do I have a photon and an electron going out? So, all right, so let me just draw the photon coming in and an electron coming in. And at the end of the day, what we need to have is an electron going out and a photon going out. And what I want to do is I want to come up with an argument why we can't draw it this way. Because I guess if all the information you have is just what I told you, the simplest thing to do is to just join them all together in one vertex, right? And that's not how Feynman diagram is drawn. Let's see, what can I don't think I can really bring in anything to say that this is wrong, other than it is wrong. But what it is the Feynman diagram, it's not just a drawing. It's not just a drawing like this. It's like a free body diagram. There are rules you have to follow because what it is, it's an outline of a calculation you are going to do if you are actual particle physicist. We are not going to do the calculation part, but because the diagram is a way of organizing the calculation, there are rules you have to follow when you are drawing them. And it turns out this is also not one of the diagrams you can draw, even though that would satisfy all the conservation laws. So I guess I need to actually tell you the rule. So I started by organizing stuff here. So, so there are certain ways symbols you use to represent agreed upon things. So there's the photon lines, and there's, how do you call it? I guess we call it fermion line. So a fermion line looks like this. And what I need to introduce is the idea of primitive vertex. It's the basic building block of Feynman diagram. It's like the smallest Lego block. And whatever bigger Feynman diagrams you have to be built out of these Lego blocks. So the primitive vertex for QED or electrodynamics, since we don't, QED is a new word, let me just call it electromagnetism primitive vertex. It will always look like this. Any portion of the Feynman diagram looks like this. You have a fermion line coming in into the vertex. You have a fermion line going out of the vertex, and that will actually end up conserving some quantity that we haven't talked about yet. And you have a photon line coming out of it. So actually, there's a kind of an intuitive sense you can make. So this is an intuitive sense that you can make. Imagine this is an electron or a charged particle. Suppose it's going in some straight line, and then suddenly it accelerates and turns the direction. When you have a charged particle that accelerates, what else happens along with that acceleration?
Electromagnetic radiation.
Electromagnetic radiation, you guys remember that? Accelerating charges emit electromagnetic radiation. We kind of talked about that when we were doing stability of a hydrogen atom. So as this charged particle accelerates, it emits electromagnetic radiation. So that's what this primitive vertex represents. So, so this one kind of looks similar to that, except it has 2 photon lines instead of 2 fermion lines. That's what was wrong with it. So here, as we draw this diagram, we have to make sure that any single vertex you look at, it has 2 fermion lines attached to it and a photon line there. Because at the very basic interaction is when a charged particle accelerates, it's emitting a photon. Or you can look at it the other way. So a charged particle is going this way, but it accelerated because it was hit by a photon. It absorbs a photon, changes its momentum, and then goes in another direction. So I guess it's kind of easier for you to see what the correctly drawn Feynman diagram looks like. So let me just draw it and see that it's correctly drawn according to all these new rules I'm telling you. So this photon and this electron, they interact at a vertex. And while I'm tempted to draw an electron that just goes out, I can't do that. I need a photon also, right? But the primitive vertex doesn't have two photons. I have, in my Lego box, I don't have any piece of Lego that has two photon lines coming out of it. So what I actually need is, need a fermion line that's going that way, and then it emits a photon going out this way. And fermion being continuing to go this way. Okay. So this is the Feynman diagram for quantum scattering, and here's a sort of intuitive, conceptual, qualitative way you can kind of make sense of what the diagram here is. It comes down to the basic representation or understanding of a scattering event. This is especially true in quantum mechanics. When you have a scattering, so I guess we are used to thinking of scattering as a single event. But what this diagram is trying to do is try to break it up into two pieces. So imagine it this way. I have a charge here. Charges are sitting here. That's going to scatter off a photon. So when a charge is sitting here, imagine an electromagnetic wave coming in. As that electromagnetic wave interacts with this, the first thing that's going to happen is this is going to oscillate up and down. So this charged particle first absorbs a photon, and as it's oscillating up and down, it re-emits a different photon. So that's what this is kind of representing, that this is the absorption, and this is the emission. Yeah?
So those are two different photons.
Now, this is where I have to be more circumspect if I'm going to tell you the actual correct facts. That, how do I put it this way? I think the best way to present a paradigm that I want you to think about is essentially, I want you to think of this diagram in three regions. The three regions are what's in this box, what's in this box, and I guess what's in between. Let me do that in a different color. What's in between. Okay? What's in this box, that seems simple enough. I think that's my initial state. And in fact, that corresponds to this initial state here. And what's in this box, that's also clear enough. That's the final state. Okay? So initially, you see a photon coming in, electron coming in. And finally, you see a photon going out and electron going out. And what's in between here is the intermediate state, or, well, let me write down the phrase intermediate. I don't think that's wrong. It's the intermediate state. And we refer to the particles that are in this intermediate state as virtual particles. And when you look at the Feynman diagram in your textbook, that's what this virtual photon refers to. And when you actually do the calculation, there are rules that you would see. I guess I don't have to throw them all at you all at once, but I think you have enough tools to understand this concept. So Kevin's question was, is the photon that's going out different photon from the photon that came in, right? And let's say we are in the center of momentum frame. so that the electron and photon, they are in a head-on collision. So they both come in with the same momentum, they collide, photon goes out this way, electron goes out this way. So the photon actually comes in with the same energy and goes out with the same energy. And you are probing with this question, is the photon that went out the same photon that came in? Let me respond with a question. Does the answer to that question matter? Yeah, if they have the same energy, different momentum, but same energy, so their wavelengths are the same, and comes down to these two are indistinguishable particles. Whether this was absorbed and then a new photon came out, or whether it underwent elastic scattering, as an observer, you wouldn't know the difference. Because in both cases, the initial and the final states you look at are exactly the same. Then, in the classical mindset, you might say this then, well, I just want to, I want to set up measuring devices, really closely look at the process that's taking place to settle once and for all, is the photon going out this or this? Then in quantum mechanical mindset, what I can say is that, well, every measurement, every observation disturbs the quantum mechanical state of the system. If you are trying to set up measuring devices to probe too closely what's going on here, you are going to alter the entire process itself. So what you really should be thinking about this is a kind of, it's a kind of black box. What's the processes that we label as virtual? We call it virtual because we cannot, even in theory, we cannot observe these processes. It's this is how we organize the calculation, and we can check what we measure with the initial and final states. But what happens in between? This is like asking where is the position, what's the position of the particle in a well before we measure the position of the particle. The quantum mechanics offers no answer. It didn't have a position. So with these virtual particles, if you're asking, did they actually exist? Well, we don't know. That's why we call it virtual. If we try to really find out, does this electron exist? By setting up some measuring system, the measuring system we set up will disturb this entire scattering process so that we wouldn't have the same process. So I guess let me leave that there. I think we can talk. We can talk more about it as we get more into particle physics. But I needed to introduce this Feynman diagram as a tool that we use to illustrate different processes. I guess the one last thing I can probably mention before we go into actually start talking about particles is how to get, if we have one known process, how to get different kinds of processes that are related to this one known process. So you have this Compton scattering, right? And I can use this to get at least 2 more processes and maybe a third. Let's at least do 2 more. So for those of you who have taken chemistry, this is what I want you to think of this as. This is kind of written like a chemical reaction equation, right? Yes? Yeah. So if this actually were chemical reaction equation, what kind of transformation can you do to the equation to get related processes?
Like any linear combination.
A linear combination. Oh, you don't have antiparticles in chemistry. You can't move a particle from one side to the other side. Yeah, so that's a bad analogy. Okay, let me not do that. So think of this like a mathematical equation, which turns A, B, C, D. Then if it's a mathematical equation, you can get other related equations by moving terms around, right? So we can do the same thing here. We can move the terms around. And I will handle some of the details that you have to pay attention to as you're doing that. So let me show you the transformed equations that shows the related processes. So I can have, well, so this is kind of symmetric. 1 photon, 1 electron coming in, 1 photon, 1 electron going out. Let me have the process where I can move one of the photons to the other side. and move one of these to the other side. Actually, sorry to keep going back and forth, but let me hold off on that until we talk about antiparticles, probably on Tuesday. For those of you who are aware of antiparticles, these are the related processes, but I think explaining that is going to take too much of the time. So the related processes here are positron colliding with the electron to produce two photons in what's known as pair production. And I thought you could also have, I guess that's it. I'm sorry, I thought I had one more process I could illustrate. But the other process that I can show is just the Coulomb repulsion. Well, if I drew that, that would be actually exactly this, but just turn the 90 degrees around. But I think to talk about pair production, we kind of need to have talked about antiparticles, so let me just do that later. Let me end this discussion of Feynman diagrams with this so that I don't leave you with a mistaken impression. I told you that this is the primitive vertex, right? So one might think, oh, then I can find a process that corresponds to this exact Feynman diagram, where I have an electron coming in, it emits a photon, and it goes out. So, that's a possible Feynman diagram. So I want to find this physical process. And I will tell you the answer. There is no physical process, no known physical process that corresponds to this diagram. Can someone kind of see why? Well, electron interacting with the photon, that's possible. Kind of comes back to this idea. Each vertex enforces all required conservation laws. Which of the conservation laws would you have trouble with at this vertex? Charge is conserved. One negative charge comes in, one negative charge goes out. So charge is good. So let me give you a principle that's going to be useful in analyzing whether an interaction is possible. So this is a principle of relativity, that when you change reference frames, that you don't change laws of physics. So if a physical process is impossible in one reference frame, it's impossible in any other reference frame. Good? You guys all take that as a true statement? Okay, then consider this. I would like to analyze this electron in its own rest frame. So I said electron coming in. Well, let's say I have an electron at rest. Then what I need is a process where this electron at rest emits a photon, and maybe it remains at rest, maybe it moves. But this is the question. Is such a process possible where an electron at rest emits a photon? Why not? Yeah, so it violates energy conservation. So an electron at rest, it cannot emit a photon because where is that energy coming from? And if you want to conserve momentum, then the electron itself has to move too. Where is that energy coming from? At its rest state, it's at the lowest possible energy. So it's impossible. There's not enough energy to emit a photon and then move. So that's why this is an impossible process. Now, if you're looking at it in a reference frame where it was already moving, then it gets more complicated. That's why I'm telling you this principle where if this process is impossible in the rest frame of the initial electron, then it's impossible in any other reference frame, even in the reference frames where calculation is more involved. Then one question that, when you actually go through calculations and actually do the analysis, then one question that's eventually come up is this. When you look at a Feynman diagram that looks like this, Coulomb repulsion of two electrons, if you are trying to draw, all right, electron coming in, electron going out, electron coming in, and electron going out, with a photon coupling this interaction together, then what you will find is that you are going to run into the same problem that we just discussed, that at this primitive vertex, that you cannot conserve energy and momentum. And I'll just give this to you as a fact that you just need to know. If mass of the photon is 0. If the mass of the photon is 0, it turns out there's no way to have this interaction work out. And so this is what I was referring to when I said, I guess last week, there are kind of ways of doing calculation that seems to allow for violation of conservation of energy and momentum. And that's something called the perturbation calculation, and the kind of traditional perturbation calculation does that. Because these three conditions cannot all be simultaneously be satisfied, in the traditional perturbation calculation, what you do is you say, all right, we are going to violate conservation of energy and hold the rest. But what that leads to is it leads to a formulation that's not Lorentz invariant, or formulation that's not compatible with the special relativity. So for people working in particle physics, the route they will take, or if you ever go into particle physics, the route you will take for the Feynman diagram, for a calculation guided by Feynman diagram, is you are going to hold on to conservation of energy and momentum by violating this instead. So you are going to say, this is a virtual photon. You are going to say for virtual particles, they are, so virtual particles are not, this is the phrase, on their mass shell. As in, so you know the properties of the real particles. Real photon has mass of 0. And in order to make this work, if and when you do the calculation, you will say, this virtual photon here, it doesn't have to have a mass of 0. It can have any other mass that it's required to have in order to hold conservation of energy and momentum. So I think that's all you guys need to know about Feynman diagram. So I'm going to be using the diagram as a way to illustrate the interactions that we are going to talk about as we cover particle physics today, Tuesday, and maybe a little bit on Thursday next week. So as we start talking about particle physics, this is a resource that I want to point out to you. It's a website of the particle data group at Lawrence Berkeley Laboratory, or pdg.lbl.gov. And the reason I want you to point out this source to you is they published a review of particle physics, and I have 2 of their publications here. Booklet, which is the condensed version, the latest one, and one that's about 4 years old. And this is the unabridged, the complete version they publish, I think, every 2 years. Let me just have this sent around, and I'm going to sound like an infomercial host for a little bit. How much do you think this costs?
Well, you said it was free, right?
$10? How much do you think that booklet cost? $10?
Why is Chinese?
Yeah, it's because they're completely free, and that's the only organization that would print it for them for free. So this is a completely free resource, even the printed versions. So you are used to PDFs being free. Like PDFs are free a lot of places. So they actually publish this on a regular basis, and when it gets published, they mail it to you for free. And I guess the idea is that they don't want people abusing it. But like the only people who would use it are people who are interested in particle physics. And it's a small enough community that they are, at least the last 2 times if you ever have to pay, let me know. So they call it order, probably to discourage people who are doing this, spammers. But when you order it, you will see that, I don't know, can I log in with mine? I don't know what address I used. Maybe, I don't know. Oh, let me just try one thing. Maybe I switched it to my regular email address. Okay. So when you order it, you will find that at least last two times I did it, I didn't have to pay anything. So I assume it's still the same. So you create an account, you order it for free, and they don't ship it to you that quickly, but it eventually gets shipped to you for free. So I just want you to highlight that because I'm pretty sure they don't tell you anywhere on the website that it's free, because they don't want people abusing it. But what I will tell you is that this is the best resource for particle physics, both in terms of the quality, because this is the standard reference for people work. They keep it updated because it's a standard reference. They compile all the published data and sort of publish one figure with the error bars. That's the established value for particle masses and whatnot. And they also send you hard copies for free, hoping that it'll be not too many people. So it used to be like American, one of the APS journals that used to do it, but I guess they started not doing it for free anymore. That's why it's now Chinese physics review that does it. Yeah. So anyways, so I want you to point out that resource for those of you who are interested in particle physics, because this is the best resource out there. That handbook is one of the best resources out there, because if you need any of the particle masses, you just look that up there. So with that, let me start talking about particle physics. So what we are going to talk about now is mostly covered in this note. So really the place I want to start out from is this statement, that we are interested in what we are going to call elementary particles, or fundamental particles, or, well, the most basic unit of matter and other things that we don't call matter. But it's just the very basic building blocks of universe are what we are interested in. And what you will find is that once that your starting point, you'll find that many of the things that you are used to thinking of as being elementary are not actually elementary. For example, elements are not elementary enough for particle physicists. As in atoms, they are not elementary enough for particle physicists because atoms are made up of nucleus and electron. The moment you can say that, it's made up of something, that's saying, oh, that's not elementary. It's made up of some smaller things. So really, these elementary particles will be subatomic particles. And you know two of these elementary particles already. So those two are, let me just start listing them. You know photon. Photon is one of these elementary particles. And you know electron. That's the other elementary particle that you already know. And you don't actually, we haven't gone over any of the other elementary particles yet. So when you look at your textbook will just throw this at you in section 1, Introduction to Particle Physics, and they will throw this at you. And what this is a summary of what's in one of these posters. It's in this poster here. And when you just look at that, the only two particles you know that are here are electron and photon. And it's, I feel that's just too much information all at once. So I want you to slowly ease you into all the particles that people discovered in the 30s, 40s, 50s, 60s, 70s. I think that's the last time the top quark was discovered or finally confirmed in lab. Oh, and wait, this doesn't have a Higgs boson is not in this list. So if you include the Higgs boson, that was discovered in 2014. Yeah.
There's two called weak force?
W boson. We'll get to that. There's W boson and Z boson, which were produced in the 70s or something, 60s. So maybe I should move away from there. All right, let's keep moving back to here. So two particles, we are going to pretend that they are elementary for us for now, because these are particles you know. And until we get to talking about hadrons or particles produced via nuclear force, strong force, this will be good enough for us. They are elementary enough for us. They will be protons and neutrons. that you have heard about, right? And the big spoiler that I have revealed right now is that protons and neutrons are not really elementary. They are made up of even smaller particles, but we can actually pretend that they are elementary because the particles they are supposed to be made up of, quarks, we have never seen a free quark. So, but let's just pretend that they are elementary for now. So this is, if you are a particle physicist living in the 20s and 30s, 1920s and 30s, this was your world. These were all the particles that you know. And your kind of starting assumption is that everything else are made up of these. All the atoms are made up of protons, neutrons, and electrons. All the interactions that you see, it's a result of a photon, electromagnetic interaction. But I guess you do have one hint of that this is not everything that's out there. It's what we were talking about on Tuesday. When you look at the atomic nucleus, if you're only dealing with electromagnetic force, there's no way that atomic nucleus can exist, right? That rings a bell for everyone? Okay. Because in an atomic nucleus, these are the only things you have. Protons would repel each other. Something is binding them together. So there's some other force that's not electromagnetic force that's binding the nucleus together. And just like electromagnetic force leads to a photon, there would be other particles that are that needed to be associated with that nuclear force. So that's something on the horizon that's going to come up. And in connection to that, I need to introduce this particular phrase or concept. It's the concept of force mediator. Or sometimes it might be called mediator boson, because they all happen to be bosons. And this is kind of why I introduced the Feynman diagram. Because the Feynman diagram, the way it's drawn, it always includes this force mediator. For example, imagine this interaction. Imagine the interaction between a proton and an electron around it, like in a hydrogen atom. Right? Now, when you look at the picture, the way we are used to handling it, do you see a photon anywhere in, well, sorry, so it's going to be an electron cloud, not in an orbit. When you look at that, do you see any photon in that particular interaction in an electron and the proton that's in the core of the hydrogen atom? We don't see any real photon, right? But in the way we handle it in particle physics, you still illustrate that interaction as being mediated by a virtual photon. So if you are drawing that interaction, you would draw them this way. So one way to illustrate mediator boson, for example, hydrogen atom. You would draw the interaction of the electron with the proton in the hydrogen atom as well. You have a proton come in. You have electron come in, and you need to have electron going out, and you have proton going out, and you just say, well, I'm trying to draw this Feynman diagram thing, so it would need to be vertex here, at the vertex electron coming in, going out, vertex here, proton coming in, proton going out, and these would be connected by a photon. So this is the virtual photon, as your textbook labels it. Or in the language that we want to use that will apply to forces that are not electromagnetic, this will be the force mediator. And just to kind of flash forward to what we are getting to later on, here, all these are force mediators. Or all these bosons are the force mediators. Mediates electromagnetic interaction, strong interaction, weak interaction. So that's a kind of a spoiler of something that's going to come in the future. The fact that we have evidences, hints of forces or interactions that's not electromagnetic means we are going to have additional force mediators. soon. But for now, let's just start out with the additional particles that make up matter, additional fermions. So these force mediators, they all happen to be boson. I don't think there's a fundamental law of physics that says they must be bosons. In fact, if you have heard of supersymmetry, the entire idea there is based on the fact that it doesn't have to be that way. And so, but the universe, as we know it now, it just happens so that all these particles that make up matter, they are fermions. Or let me just call them matter particles. So what I want to give you a long introduction to is how other matter particles were discovered. Because these are kind of a normal, usual matter particles that you are familiar with. You've seen them since chemistry. And the matter particles that we are going to talk about now are the ones that were discovered either by accident or by people just pondering things in the elementary interactions. So let me start out with the discussion of beta decay, which is what we were talking about last Tuesday. And I asked you to hold then to believe in this fiction that in a beta decay, this was all we had. So this is the fiction that we were looking at last time. So what's a beta decay? Like what phenomenon or interaction are we referring to in a beta decay? Yeah, so beta rays are electrons. So beta decay is a nuclear interaction which ends up with a process that ends up with the emission of an electron, right? And the particular process that we are looking at was where a tritium, hydrogen 3, goes into helium 3 and emits an electron. That's what we looked at last time, right? And now that we are talking about elementary particles, let me give you an even more elementary version of it. It's not as easy to set up an experiment for reasons that I'll explain. But what this is, let me represent it in a more, in terms of the elementary particles. What this is one proton and two neutrons, right? Going into helium-3, or two protons plus one neutron and an electron. So you have what's sometimes known as spectator particles. Particles that are not really doing anything. That's just there to spectate. So let's get rid of those spectator particles. I have one proton here that, that's apparently not doing anything. And I have one neutron here that's apparently not doing anything either. So get rid of that. So at the very basic elementary level, what you have is one neutron turning into a proton, in the process emitting an electron. Okay? So that's the very elementary representation of what's happening here. Neutron becomes a proton emitting an electron. And if we were to try to draw a Feynman diagram, it might look something like this, which is not going to look like the elementary vertex for electromagnetism because this process is not happening by electromagnetism. There is no electromagnetic process that would turn a particle into another particle. So, but let me just draw a kind of rudimentary version of a Feynman diagram. It would be, I have a neutron coming in. That neutron turns into proton for some reason, and it also emits an electron in the same process. And this is the vertex where all of that's happening. Good? Questions? So this is a new type of interaction, new type of primitive vertex, new type of stuff. So we are not going to hold this to, this must be broken down into electromagnetic primitive vertexes. We don't need to have that because it's an entirely new interaction. But the one rule we want to still hold up is that at this vertex, all conservation laws must hold. Right? And last Tuesday, we actually looked at one consequence of holding to this conservation of energy and momentum. Do people remember that calculation we ended with on Tuesday? So, like, what was the conclusion we came to looking at decay of tritium into helium-3 and electron?
Like the recoil energy can almost be ignored. So all the
Yeah, that's one. And we calculated on electron energy, right? So the consequence of holding to conservation of energy momentum is that this is actually a general rule. When you have a single particle that decays into two particles, then these two particles must have definite energy and momentum, right? Because there's no other possibility. But when people were actually doing careful measurements with the beta decay, actually measure the energies of these outgoing electrons, this is what they found. So this is actually a plot of tritium decay that I not borrowed. I'm doing it properly because I actually cite the Catherine collaboration that published it. So this is the plot of the beta energy of tritium decay. So beta energy meaning energy of the electron that's coming out of the beta decay. And this is what they measure. I mean, this is the kind of modern, very refined version, but this has been known since the 30s, 20s, since people started looking at beta decay. You have a beta spectrum. The electron comes out with a spectrum of energies. In fact, the most likely energy for so this 18 kilo electron volt is what we calculated on Tuesday, right? But electrons, very few actually come out with the 18 kilo electron volts. Most of them come out with a fraction of that, 3 kilo electron volts. And so this is a kind of a crisis because the calculation we did on Tuesday, we didn't assume a lot there. The only thing we really assumed was that whatever this interaction is, energy and momentum must be conserved. And the result we derived on Tuesday, what the result was demanding was that this spectrum of electron energy must be flat and then peak at 18 kilo electron volts. That's the spectrum that our calculation was predicting, and this is the experimental plot. So it's a kind of a crisis, and that's when you're in a scientific crisis, that's the exciting time to live in. That's when you get to propose new ideas and have people test it or whatever. So there are multiple competing proposals. One of them came from Niels Bohr, which I talk about in this thing. One of the proposals of Niels Bohr was he was suggesting maybe energy conservation isn't held strictly in quantum mechanics. And you have to understand this was in the 20s, 30s. People didn't really understand quantum mechanics. Einstein, who got Nobel Prize for photoelectric effect, he never subscribed to Copenhagen interpretation of quantum mechanics. So even Einstein was having difficulty with correctly understanding quantum mechanics. So, and what I will tell you is, skip to the modern times and tell you is that he was wrong. That when Niels Bohr suggests that maybe energy and momentum is not conserved in beta decay, he was just flat out wrong. But it remains that you still have to explain, like if energy and momentum is conserved, like what could we have missed? What could we have missed that what the experimental result we are getting does not agree with our theoretical calculation?
it may release something else.
Yeah, we might have missed something literally. There might be a particle that we could not detect. This was the proposal by Wolfgang Pauli of Pauli exclusion principle. And so what Pauli suggested was we actually literally missed something. So in these outgoing particles, there's one more particle there that we literally missed. So today we call it neutrino. And in fact, I'm being very specific about it. It's actually an antineutrino. Specifically, it's an electron antineutrino. But back then they weren't making this distinction, so let's just call it neutrino for now. It's just a placeholder for a particle that they couldn't see in the 30s, but they were guessing, well, maybe we need to, one particle going into two that leads to a prediction that just doesn't hold. So maybe there's one more particle that we are going to call neutrino that's going out. And turns out he's correct. And in fact, there's, even with what little we know, we can actually kind of get at why this is correct. For one, does everyone, so to clear off the kind of big things first, does everyone see that this hypothesis would solve the issue with conserving energy and momentum and still getting this spectrum for electron? Like, you can see that? Kind of, you can see if I have 3 particles going out, then now I have enough degree of freedom. I could have put all the kinetic energy onto this neutrino so that electron comes out with 0 energy. Or I could somehow arrange things so that this neutrino comes out with practically 0 kinetic energy. Then, so that I have this, this maximum possible energy that the electron could have in the absence of the neutrino. And so, you know, introducing this neutrino solves that beta decay spectrum problem. And it turns out there's additional problems that this neutrino solves that people in the 20s and 30s didn't know back then. But I think you guys actually have enough information to kind of figure this out with some guidance. So I said all conservation laws must be satisfied at this vertex. But we've been talking about only 2 conservation laws, energy and momentum. We haven't talked at all about the angular momentum. And you know, back then they couldn't because they knew nothing about the spin angular momentum, but we do. So we can consider if we didn't have this neutrino, if a spin angular momentum could be conserved. Yeah? What's the spin angular momentum of the electron? Half, right? It's a spin-half particle. We went over that like last week. So electron has a spin of half, let me call it h bar. Does anyone here know the, so we didn't explicitly talk about it. Does anyone here know the spin of proton? No? Well, you can kind of guess. I call the proton a fermion. So it must be some kind of spin-half. It turns out it's exactly spin-half. And I think back then they actually knew proton was a spin-half based on measurements with the hydrogen atom, because both of them being spin-half makes the hydrogen atom's overall angular momentum to be either 1 or 0. And if you've heard of like para-hydrogen and ortho-hydrogen, wait, is that it? I'm not entirely sure. Never mind. So these are spin-half particles. So I guess the excuse for the physicists in the 20s and 30s is that they didn't know much about neutron. So they didn't know the spin of neutron. Well, now we do. Neutron is a fermion. So what do you guess is the spin of neutron? Also half. So these are 3 spin-half particles. So imagine, just imagine that we didn't have this neutrino, that this is all the interaction we had. Do you see any issues here? Right? What do you get when you add 2 spin-half particles? I know I said that it was optional last Thursday, but the result of our calculations last Thursday is that with the 2 spin-half particles, you could get spin 0 or you could get spin 1, right? Well, this is neither. So this interaction, unless there's a third particle, doesn't conserve angular momentum. So what addition of neutrino does is it saves angular momentum conservation in this reaction. So once people figured that out, then this neutrino was actually accepted pretty quickly. But so Pauli suggested the idea of neutrino in the 30s, 35 or something. And the neutrino actually wasn't detected in a direct measurement until 1950 something. And but you know, in that intervening 2 decades, people weren't really questioning that this exists because having this neutrino exist solved an additional problem of angular momentum conservation. Question?
Never mind.
Yeah.
I figured it out.
So there are actually some properties of neutrino that we can infer from all the conservation laws that must be satisfied. And that's probably something we should go over so that maybe that's what your question was, no?
No, my question was why do we detect photons all the time, but we don't detect neutrinos? But then I forgot photons are in the electric field.
Yeah. So it interacts with the charge. So photon, they themselves don't have a charge, but they interact with the charges. Yeah. So let's just list the possible properties of neutrino. So I guess one thing is kind of comes out of this discussion here. What's the spin of a neutrino? Yeah, it's a half spin particle. So it's a spin half particle, which means it's an additional particle we can now add to this list of possibly elementary particles that belongs with the fermions. So, all right, so we have a neutrino here. That's one more particle that we didn't know existed. And back then in the 30s and 40s, they still haven't detected it. But there's a compelling argument to say that it actually is there. Any other properties of neutrino that it must hold? Kind of based on the descriptions, observations? Electrically neutral. Kind of in the name, but I guess that's circular reasoning. So the reason it's electrically neutral is because somehow we are not seeing it. So if it were electrically charged, then we would have seen it. So that's really the argument for why neutrino must be neutral, because it's sort of like, so it must be electrically neutral. And there's one more thing that's not immediately obvious, but to an experimentalist who's making careful measurements, they could have eventually kind of inferred from their data. And it comes from here. This is where it's a numerical argument. So you kind of have to have trust in the numbers you're working with. So it's the fact that this 18 kilo electron volt is the theoretical number you calculate with no neutrino. And there are electrons with about that much energy. So that means whatever rest energy is in the neutrino must be pretty small. Because if a neutrino had to take up significant rest energy, then you would see this curve come short of this 18 kilo electron volts. So based on that, what they initially guessed was that they were massless. But this is actually a fairly new development in particle physics. The last conclusive evidence was only discovered in 2001. And it turns out it's not massless, but it's, I guess I can say, it's nearly massless. And the kind of experiment that Catherine collaboration does, which is still active collaboration, is they're still trying to determine the mass of neutrino. And there are theoretical reasons why neutrino must be only nearly massless, not exactly massless. But I think we'll skip that, only to show you plot that illustrates what kind of measurement this Catherine collaboration is trying to make. I think I need to scroll down. So once again, this is all optional. I wouldn't test you anything that's here. That's not also in your assignment. So blah, blah, blah. And so this is what they're trying to measure. And I'm pretty sure this is still plot from Catherine collaboration. That's why they were publishing this at all, because that's what they're trying to measure. So you see that little, so this might still be a two plot, but what they are plotting here now is a kind of different version, hypothetical plots. So this blue curve would be if the neutrino was exactly massless, and this red curve is if the neutrino had a mass of 1 eV. And I think the current upper limit on the electron neutrino mass is 2 eV. So like 1 electron volt out of a energy measurement of 18,000 electron volts. And if this is a possibility, if a neutrino has mass of, I guess, is that 0.3 eV or something like that? So this is in the field of what's called precision measurement. And they are trying to, not so much test, because we kind of know that some flavors of neutrinos that must have mass. They're trying to determine, okay, so what is that much mass for the electron neutrino? So neutrino is the very first of new particles we have to add, because in order to explain beta decay and the features observed in beta decay, we need to hypothesize existence of a new particle. I guess with this particle, this is probably a good place to introduce new conservation laws that I haven't mentioned at all because there was no chance for this to come up, but this is a good place to mention 3 new conservation laws. So 2 of them are exact conservation laws. Those 2 exact conservation laws are the conservation of what's called baryon number. And I'll explain that. And the second one is similar to this one. It's a conservation of lepton number. And the last one is only an approximate conservation. It's a conservation of what's called, so I think I mentioned this, physicists to become more creative in naming things. Baryons and lepton, those are not all that creative. I'll explain why they're not all that creative. This one is, it's a conservation of something called the flavor. And I just have to tell you, it has nothing to do with the flavor. It's like, how are you going to taste the neutrino? But this particular property has been named flavor by the whimsical particle physicists. So I guess how many here know Greek? So these numbers are baryon and lepton. They come from Greek. The etymology is Greek. And what baryon means is a heavy particle. The on is the ending for particles. Baros is, I think, like weight or like heavy, whatever. And lepton, I don't know the actual root word, but it's the light particle. And of these particles, you know the difference between protons and electrons, right? Proton has mass of approximately 1 GeV per c squared, and electron has a mass of approximately 0.5 MeV. Let me use MeV. So proton has a mass of approximately 1,000 MeV per c squared. Electron has mass of approximately 0.5 MeV per c squared. So you see the pretty big gap between these. And in fact, the proton and neutron has a pretty similar mass. Not the same, because if they were the same, this wouldn't be possible. So neutron is a little bit heavier, but they have similar mass. So the initial classification that people came up with is that they were calling these as the heavy particles, or baryons. And they called electron a light particle, or lepton. So with the idea of these 2 conservation laws, let's come back and look at this here. When you look at this interaction or this diagram, is the baryon number conserved? Right? 1 baryon came in, 1 baryon went out. Is the lepton number conserved? Not really, right? I had 0 lepton come in. Before neutrino, I had 1 lepton going out, which is troublesome enough. Even with the neutrino, it looks like I have 2 leptons. So neutrino is a nearly massless or a light particle. So let's say neutrinos are also leptons. But that doesn't really fix my issue. I have an electron going out and I have a neutrino going out. So this is an anti-neutrino. How many here are familiar with the concept of antiparticles? Not enough of you. So let me just draw the diagram for anti-neutrino, and I will do a little detour of discussion of antiparticles. So these are the symbols we use to indicate antiparticles. It's for the particle, the typical way to indicate it's an antiparticle, we put a bar over it. So that means it's anti-neutrino. So this is anti-neutrino. And in Feynman diagram, we already indicate passage of time from left to right, right? Which means these arrows are actually redundant if all you are trying to say is that that's the direction that the particle is going. So really what these arrows are used for is to indicate, is it a particle or antiparticle? So with the neutrino, it'll be drawn this way. So antiparticle coming into the vertex. So you have a plus 1 lepton number going out, and you have minus 1 lepton number going out for a total lepton number of 0. Yeah? So I guess I need to talk about antiparticles. I want to kind of introduce and finish talking about antiparticles in 5 minutes. And what's the quickest way to do it? How many people here have heard of the phrase positron? Maybe. Positronic brain, science fiction, never mind. So positron is an antiparticle of electron. It was the first antiparticle to be discovered. Let me show you the experimental basis, how positron was originally discovered in the first place. So discovery of positron. There's an iconic image for discovery of positron. So I guess this is probably good. It's from Wikipedia. So this is an iconic image. Wait, where's my iconic image? This is the iconic image for the discovery of positron. You might look at it, what are we talking about? This is, so let me try to kind of describe what's going on here. So one feature I want you to pay attention to is this curved path. You see the curved path, right? Yeah. So it's the curved path. It is the measurement of trajectory of a particle. This is a measurement taken in a device called a bubble chamber or cloud chamber. It's a device used to visualize paths of particles. It actually literally visualize. So now it looks curved. Why do you think it's curved? There's a magnetic field. They put this chamber inside the magnetic field for the explicit purpose of trying to measure the charge of the particle, because what you saw with alpha, beta, and gamma rays was that was one way of discovering charge of the particle, right? So it's in a magnetic field. And based on the picture, the way the magnetic field is supposed to be set up, I think the magnetic field was set up so that you had a magnetic field that was going into the board. All right. So suppose that you have a particle that bends this way. You have this trajectory of a particle that bends this way. Now, let's suppose I told you that this particle is electron. Then let me ask you this question. What direction is this electron traveling in? Downward, right? Because V cross B, that way goes to the right, but the electron is negatively charged, so the force actually points to the left, so that would be consistent with this leftward curve. So if this was an electron, then it would be moving downward. So, okay, so far no discovery. So that's the reason for the placement of this plate here. The purpose of this plate here is to slow down the particle. By slowing down the particle, you can infer what direction the particle was moving. So instead of starting out with what is the particle and then determining its direction of motion, you can look at, well, what direction was it going? And from that, and knowing the magnetic field you set up, infer the charge of the particle. So let me erase all these notations and just have you look at this trajectory with that background information in mind. what's the charge of, what direction is the particle moving? So how do you know it's moving up?
The slope is greater.
Yeah, it curves more quickly here, right? And if you do the calculation, what that corresponds to is that this has less momentum. It's moving slower, that when you go through the calculation, it results in a smaller radius of curvature. So the particle is moving slower than here, which means for that to happen, the particle must have went through the plate this direction, and in the process, it lost some kinetic energy, slowed down. So knowing that direction of velocity, what's the charge of the particle? Positive. So this is the discovery of positron. That's how they discovered the positron. Now, so I'm kind of starting the story from the middle. So obviously this is an apparatus set up explicitly to look for positron, right? Then the question, why were they expecting this new particle, positron, an antiparticle of electron? And I guess I don't really have time to give you the full story. So I will just tell you that this is the kind of quick version of it. These antiparticles, they were predicted by Dirac. That's the name of the scientist, or P.A.M. Dirac. I think a P stands for Paul, I'm not sure. Well, P.A.M. Dirac. He's credited with coming up with something called the Dirac equation. It's the relativistic quantum mechanical equation that applies for spin-off particles. And one of the prediction of a Dirac equation is that you need to have a negative energy state. And the way linear algebra works out for relativistic quantum mechanics is you cannot simply say the negative energy states are unphysical. That's not allowed for you. It's kind of for the complete spanning of the space of the solutions, you need to allow negative solutions. So what Dirac suggested was that the universe is filled with what's called Dirac sea of electron states. So there's up to some particular level of energy levels that's filled up with the fermions already. Then due to exclusion principle, those negative states that are allowed in the solution, but the actual negative energy particles cannot exist because it's all already filled up. And then the existing electrons with the positive energy are the states above this Dirac sea ground level. And what he contemplated was excitation of one of those negative energy states into positive energy. Then what you would have is, I have this Dirac sea that's all filled up. So when you excite one of these filled up states into positive energy state, this is what you would have. You would have a real electron that we are already familiar with, and you would have this hole that's left by the state that was excited up to here. This could happen by a photon being absorbed, for example, and what this hole would get referred to is the positron. And it actually, because it's the absence of a negative energy state, it actually does have positive energy. And so that's where the prediction of the antiparticle comes from. And so it was predicted, people went out looking for it, they found it, antiparticles exist. And I guess the easiest way to think of as antiparticles, it's the same as the particle, except that it has opposite charge. And certain quantum numbers it has, like lepton numbers, are also negative. So that's where this neutrino is, instead of being a neutrino, it's an anti-neutrino. So that's where that comes from. I guess let's leave this there. And as far as the flavor conservation goes, so it turns out there are 3 different kinds of neutrinos. There's one associated with electron, and we are going to eventually introduce two more leptons. So far, you know only one. Up to today, we know of 3 different kinds of leptons. So we'll introduce them eventually, but for now, this neutrino that's involved here, it's the one that's coupled together with the electron.